Okay, welcome back. This is 9.6, more with probability and counting. 9.6 in particular, we're looking at R combinations with repetition allowed. Oops. So up to this point, we can kind of categorize what methods we've been using. So we'll say repetition on one side, one hand here, whether it's allowed or not. Repetition, so yes versus no. On the other hand, there's order. Does order matter? And again, it's yes versus no. And we can kind of turn this into a table and then look at all the different methods that we are kind of using. Okay. So when order matters and there's no repetition, that's the permutation type. So R permutations. In other words, we have the formula P and pick R. Okay. When order doesn't matter, but so sorry, repetition no, order yes. Okay. So when order doesn't matter, but and there's also no repetition, that's the C, the combination, R combinations. Okay, so C and R. When we start throwing in repetition and order still doesn't matter, so the top right part of the chart there. So repetition yes, order no, that's what we're going to look at in this section, R combinations with repetition. And if you think of NCR as kind of in the other notation, well, let's write it out the way it'll be. So it'll be n minus 1 plus R, choose R, which we'll do in this section. Okay, if order matters and you're allowed to do repetition, we kind of see that a little bit with the problems like the millimeter. How many ways can you reorder the letters of the word millimeter? You know, that would be order matters and repetition, kind of, but there's a restriction on the repetition. If there's no restriction on the repetition, so you can, you know, literally use a letter or a number as many times as you want, that will just be the number of I don't know, letters or elements that are available to the power of how many letters in your word that you're looking at. Okay, so n to the k, you can think of it that way, but it's also that other kind of case where we were dealing with like n factorial all over maybe n1 factorial times n2 factorial, where that was kind of the how many different ways can you order the letters of the word milliliter. You know, you have to divide out because there's two L's in there. You have to milliliter. Actually, there's like three L's, so you have to divide by 3 factorial. So hopefully you remember those problems. Okay. Anyways, it's a good idea in general, at least in our homework, at least it's, you know, it's kind of ordered. And you know, if you're in a particular section, you're using a particular formula. But in the real world, you kind of have to figure out which part of this box you're really in. Okay, so it becomes necessary to categorize everything, and this it's given in the book and the last, like on the last page of 9.6. Okay, this little categorization chart. All right, so anyways, today the section of this chart that we're worried about is this upper corner here. So we've worked with NCR, which it counts the number of subsets of a set of n elements. So the number of subsets with R elements taken from a set with n elements. Okay, so anyways, let's take a look at what we have today. So multi-sets, and in particular here, order does not matter. But repetition is allowed now. Okay, so in particular then, let's maybe look at an example to help us along. This is like the kind of one of the examples in the book. What we need to do is list all the multi-sets size 4 from the given set 1, 2, 3, 4. Okay, so the deal is, and when you're dealing with sets, order doesn't matter. So when you talk about NCR, usually you're talking about a number of subsets or something like that. Here it's kind of the same idea. We're looking for a number of subsets, but now we're allowed to repeat elements. Okay, so that's what they're going to call them, multi-sets. Okay, so one multi-set of 4 elements from that set is just 1, 1, 1, 1. Okay, and then you can have 1, 1, 1, 2, and then you could have 1, 1, 1, 3, and then you could have 1, 1, 1, 4. Right, so this are all the sets where the first 3 elements are 1, or you think of it as 3 elements being 1, and just trying to make the point of what we're dealing with. We're not including now, when we do our enumeration, we're not going to include 2, 1, 1, 1. We're not going to include 1, 2, 1, 1. Okay, order doesn't matter, so we're throwing out all of those guys. Okay, all right. I'm just trying to, at this point, find a way to enumerate these objects, right? So I could say, let's now look at all of the ones where there's just 2 ones. Okay, so 1, 1, and then we have we can have 2, 2, 1, 1, 2, 3, and then 1, 1, 2, 4. Okay, and then 1, 1, 3, 3, and then 1, 1, 3, 4, and then 1, 1, 4, 4. Okay. It may not be clear. If the computer programmers amongst you might see kind of how it's working, and when we look at a certain type of program with nested loops, it will enumerate for us these multi-sets. Okay. Let's keep on moving here. Now I'll look at the sets with just 1, 1. So that would be 1, 2, 2, 2, 1, 2, 2, 3, 1, 2, 2, 4, and then I can kind of increment that 2 to a 3, right? The third 2 there, make that a 3. So 1, 2, 3, 3, 1, 2, 3, 4, and then I'll increment that 3 to a 4. So I'll have 1, 2, 4, 4. Okay, and you could, it's going to take a while, but you could kind of enumerate them all in this fashion. Okay, so ultimately you would have like 3, 4, 4, all the ones with 3s in them, right? With 1, 3. So that would just be 3, 4, 4, 4. That wouldn't be all the ones with just 1, 3, would it? So you would have like 1, 2, 4, 3 is also in there, but using my enumeration program, the last 2 would be, and I don't want to go through the whole program, right? So I'm going this dot, dot, dot. There's all kinds of stuff in there, but my last 2 were 3, 4, 4, 4, 4, and then 4, 4, 4, 4. Okay, but anyways, what I'm looking for is kind of an easier way to count all these up without having to go through this kind of almost arbitrary ordering that I've formulated here. And the way it will work is the following. Okay, so the way to format this discussion and the way to figure out the number of arrangements that we're dealing with is to kind of think in terms of buckets. Okay, so you'll have a bucket for the ones, you'll have a bucket for the twos, a bucket for the threes, and then a bucket for the fours. Okay, and all you do every time you enumerate, every time you kind of list a number, is you're putting x's inside these buckets. So the number 1111 is just this. Okay, so that would equal 1111. Okay. Another example then, 2, 3, 4. Let's just take 1134, right? How would I write that in this new kind of way? So that would be 1, 1, and then 3, 4. Okay, so 1, 1, 3, 4. Let's make this even more abstract. So I don't need to draw out the buckets. Okay, all I kind of need are like lines between the buckets, right? So there's lines, and then this is anything I put over here is in the first bucket. So if I put 1, 1, that's like that. 2, and then 3, and then 4. Okay, so I could rewrite 1134 as shown here. So that would be 1134. So 2 x's slash, and then you could kind of smush them all together, right? So another way of writing that would be xx slash slash x slash x, and you could do that transformation, right? So what we're kind of doing is building an abstract picture for these numbers, a way of symbolizing or encrypting, I guess. Okay, so let's take another number and see if we can encrypt it, kind of. So let's take 1, 2, 3, 4. How would I write that in this new notation? Okay, so 1, and then I need an x in the 2 slot, and then an x in the 3 slot, and then an x in the 4 slot. So it would be 1, 2, 3, 4. How about 1, 2, 2, 4, right? 1, 2, 2, 4. And hopefully you'll agree that I can take any number in this listing above, which is a list of every possible multi-set taken. So these are 4 element subsets with repetition allowed taken from the set 1, 2, 3, 4. Every one of those elements can be written in this form where you have 4 x's and then 3 bars. Okay, so you could just go x slash x. As long as you have 4 x's and 3 bars, you're good, right? So we can transform this into 1, 2, 2, and that's the one I just wrote. Sorry. So let's go 1, 1, 1, and then 1, 2, 3, 4. What number is that? Oh, that's 4, 4, 4, 4. Okay. So ultimately, what we're doing when we enumerate all of these different multi-sets is finding all the different combinations of. So we are finding all different words, I guess in quotes, based off of slash slash x x x x. So we're finding all possible arrangements of that, right? And we kind of already did that. That fell into this above category. This let me circle it in red. It's kind of this category, right? So order matters, but repetition and repetition matters as well. And the corresponding section that we were looking at were problems like how many different ways can you enumerate to write these words with repeated elements, right? So I don't know, say how many different ways are there to write the word book, right? So what would that be? It would be 4 factorial all over, and then you divide by repeats, right? So we have 1, 2 zeros being repeated. B, there's only one of those, and K, there's only one of those. It was that kind of formula that we used. So in our example, so in this case, what do we have? We have 4 x's and then 3 slashes. So you'll have 3 plus 4 factorial all over, and then there's the 3 repeated slashes and the 4 repeated x's, right? So that's going to end up being 7 factorial all over. Let's rearrange this as 4 factorial times 3 factorial. Okay, and I do that because ultimately I want to rewrite it in this NCR notation. So in that case, it's going to be written out in kind of all of its glory. What do we have? We have the number of x's that we're putting in. We're going to call that r, and then we're adding that to the number of slashes. And the number of slashes, and the way we constructed it, is just 1 less than the number of kind of boxes that we're putting in. Okay, and the number of boxes is just the number of terms, or the number of numbers in this particular number, right? So in that case, the number of numbers in the set that we had was 4, and then we subtract 1, so we only had 3 slashes. And let me erase the r. I didn't mean to put in the r already. And then plus the number of x's, which in this case was 4, right? And then choose 4, basically. Okay. So 8 minus 1. So in general, if you can accomplish this kind of transformation into x's and bars, if you have n bars or slashes and then r x's, the formula you use is going to be n minus 1 plus r, choose r, okay, which is the formula that I kind of put in the box here that you probably, in the blue here, that you aren't as familiar with. Okay, so that's pretty much what you do in this whole section. You're kind of trying to find a way to think of these things in terms of bars and x's and kind of filling in slots, right? This formula is not something I would memorize. I mainly, when I go through my problems, I think in terms of, again, the slashes and the x's and just filling in the boxes. Okay. For the computer programming problems, you're probably going to have to use this formula, this n minus r plus r, choose r. Anyways, let's take a look at some examples. Here's another example. A party wants to set out 15 drinks with only 5 types of drinks. Okay. So they're putting out 15 drinks, and there's 5 different kinds of drinks to choose from for each. So they're setting out 15, and in their, I guess, behind the doors, they have 5 types of drinks to set out. Okay, so a party sets out 15 drinks, right? The people setting out the drinks choose from 5 different brands. Okay, so order doesn't really matter here. So if you can imagine, you're putting out 2 sprites and, I don't know, 3 pops. It doesn't matter if you go three sprites and let's say you're putting out 2 sprites and 3 Cokes, right? 2 sprites and 3 Cokes. So repetition is okay, but order doesn't matter, right? Because putting out 2 sprites and 3 Cokes is the same as putting out, you know, Coke, Sprite, Coke, Sprite, Coke. Okay, so this is one of these multi-set problems. Okay. Okay, to think of it in terms of putting boxes, the slashes and the X's. So we have basically 5 different boxes that we're putting stuff in. So you use 4 slashes, right? Here's brand 1, maybe it's Sprite. Brand 2 is maybe Coke. Brand 3, Mellow Yellow. Brand 4, Royal Cola. Brand 5, whatever. Okay, and then you're putting 15 out. So you have 15 X's. So maybe you have 3 of brand 1, 3 of brand 2. Maybe you don't like brand 3, so you don't put any there. And then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of brand 4. So people like brand 4. And I think I have too many. Whoops. So I can get rid of a couple of those. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. 8 brand 4. And then 1 brand 5. So that would be one possible distribution of drinks. Okay, so part A, how many different distributions are there? How many different combinations of drinks are there? Okay, well, just think about how many X's you have. So it's going to be the number of slashes plus the number of X's. Choose the number of X's. If you really want, you can think, well, it's the n minus 1, which is 5 minus 1, but that's 4. That's just going to be the number of slashes. Okay, there's 1, 2, 3, 4 slashes. Right, that's the 5 minus 1 part. And then you're adding in R, and R is just the number of X's. Okay, so in this case we have 15 X's. And then choose R, so that's also going to be 15. And then that just gives you your answer. Okay, I don't overthink it too much. Just try to take it for what it is. 15 plus 4 is 19. Choose 15. Okay. Okay. Part B. How many have at least 6 root beers? Okay. How many of these combinations have at least 6 root beers? Okay, it's almost like you're throwing away X's in this regard. So you have your categories set up. In other words, you have your slashes, and then you're basically saying, all right, 6 of the X's have been distributed already. Okay, so you're throwing out 6 X's essentially. If you want to, you put them in the root beer category, whichever category is root beer. I don't know. Let's say the 4th category is root beer. So what do you have left over to figure out? Well, you have, so originally you had 15 X's, and now you're saying you've already used 6 of them. So you have 9 left. So in your counting, what you're doing is saying, all right, still you're thinking of 5 minus 1 categories, or basically those 4 slashes, 5 categories minus the 1. And then you're adding in the 9 X's, and then you're going choose 9. Okay, so at the end of the day, that'll be 14 minus 1 is 13. Choose 9. Okay. Okay, so the main problem they're going to worry about then is kind of the complement of that problem, which is a bit more tricky, but if you use subtraction, you figure it out kind of easily. So they want to know how many combos have 6 or less root beers. Essentially what they're saying is that, how many combos have 5 or less? So they're saying the store only has 5, the back room only has 5 root beers left. Okay, how many of these combinations can you make given that you only have 5 root beers to distribute? How many combos have 5 or less root beers? Okay, so it seems like it's a little bit harder of a problem, but the way you're going to kind of do it is to say, all right, 5 or less is just the difference between the total number of root beers and the number with 5 or more, or 6 or more. And the way these problems are usually set up, you just use the information from the previous parts to get your answer, right? So we already have the total from part A. That was 19, choose 15. And then the one with 6 or more was part B, and that's just 13, choose 9. And then that's your answer. Okay, other types of problems. Figuring out ordered triples, the number of ordered triples. So we want to know the number of triples that are just lists of 3 elements, I, J, K, where I is greater than or equal to 1, and then I is less than or equal to the next number, and then J is less than or equal to the next number, and we presume that the last number is less than or equal to some number, we'll say n. Okay, so how are we going to pull this off? Well, we basically have n different numbers to choose from, right? So you'll have, in the case, let's consider a concrete example. So let's say n is 5. In that case, you have 5 buckets, right? Or 4 slashes. And then you're just putting, so 1, 2, 3, 4, 5. You're just going to put X's in those buckets. So one ordered triple, and we only use 3 X's, right? Because it's a triple. So that ordered triple there is 1, 3, 3. Okay, and note it follows the restriction with the inequalities. 1 is less than or equal to 3, and 3 is less than or equal to 3, and then 3 is less than or equal to 5. Okay, and of course I is greater than or equal to 1. Okay, so let's look at another one. So slash 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 slash. Let's say boom boom and then boom. Right. So that ordered triplet would be 2, 3, 5. Okay. So what we're doing is, in this case, we have 5 minus 1 plus the number of x's, which is 3, and we're choosing 3. Okay. So that would be 7, choose 3 in that case. But in general, what's going on is we're having n boxes to fill in. And then for the slashes, we subtract 1. And then plus 3 because it's an ordered triplet, and then choosing 3. Okay. The book or the exercises in the software may ask you to get an actual expression for this. So n minus 1 plus 3 is n plus 2. Choose 3. And then you could use your definition for NCR. So this is n plus 2 factorial all over 3 factorial times n plus 2 minus 3 factorial. Okay. That'll equal n plus 2 times n plus 1 times n minus 1 factorial, just using the recursive definition to expand that, divided by 3 factorial times n plus 2 minus 3 is n minus 1 factorial. And then you see there's a nice cancellation. Goodbye, goodbye. And we have this expression, n plus 2 times n plus 1 times n divided by 3 factorial, which is 6. Okay. Okay. Now we come to the programs. Okay. So we have a triply nested root. Triply nested sort of program. Okay, I don't know what the heck I just said, but there we go. Okay, so k equals 1 to n. Okay, and then the next loop, inner loop, j will go from 1 to k, and then the next inner loop for I going from 1 to j. Okay. And then it executes some code. and then it jumps out, right? So next I, next J, and then next K. And what would happen here is it should give us an ability to enumerate the multi-sets. In this case, this will be sets of elements size 3, okay, where you're picking numbers from 1 to n. Okay. You can tell how many x's you have based off of the number of loops. Okay, so if you have 3 loops, you have 3 x's. And the number of boxes you're putting the x's in will just be the upper index on that first loop, this n part. Okay, so in our case, knowing nothing else, okay, the expression should be n minus 1 plus 3, choose 3. Okay, which is exactly what we got, what the last one was. Okay, so that's just going to be in its final form. What is it? N minus, or rather just n plus 2 times n plus 1 times n all over 6 operations. Okay, so knowing nothing about it, that's the deal. But let's say we want to be a little bit more careful. Maybe it's a different, not exactly this kind of code. What's the best way to go about doing it? I would say just go ahead and do a trace table, right? So you have K, you have your J, and then you have your I, right? Okay, so in that case, let's take a look at what's happening. So K starts at 1, okay, and then you have J going from 1 to 1, and then I going from 1 to 1. Okay, so J is initially set to 1, and then I has to go from 1 to 1. So it goes from 1, and then it's done, right? Next I, there is no next I. Next J, there is no next J. And then you go next K, right? So next K is 2. So now J is going from 1 to 2. So it starts at 1. And then when J is 1, I is going from 1 to 1. So it goes to 1. And then next I, there is no next I. So it goes next J, and the next J is 2. Okay. So now I is going from 1 to 2, starts at 1. And then it goes to 2, right? So next I, there is no next I, so you go next J, there is no next J, so you must go to your next K, so that would be 3. And then these J's are going from 1 to 3, okay, it's starting at 1, so when it's at 1, I is going from 1 to 1, so it just goes 1. There is no next I, so you have to increment to the next J, which is 2, and that will reset the innermost loop to go from 1 to 2. So I'm going 1, and then the next loop it'll go to 2. 3, 2, and then as soon as it hits 2, it's kind of done, and it resets, and it's going now from 1 to 3, and you have to reset J as well to 3, and so on. So this will be 3, this is 3, and now it's going 2, and then it'll go up to 3, right? Let's just do one more. So now I has nowhere to go, J has nowhere to go, so I increment K up to 4. Okay, that resets J to be 1 to 4, and in particular, at that point, I would be 1 to 1. Okay, so as soon as I goes to 1, it's done, and then it steps out, and I have to increment J to 2, okay, and reset I so it goes from 1 to 2. So it's at 1, and then it goes to 2. Okay. So there's no more I, so I step out and I have to go to my next J, which will be 3, and that'll reset the inner loop to go from 1 to 3. Okay, so okay, hopefully the pattern, you know, I mean my English is not so good. Hopefully the pattern is becoming more and more obvious as to how this is working. Okay, so at this point, I'm at 4, 3, and then I has to go 1, 2, all the way up to 3. Okay, and then once it hits 3, it'll push up the guy right above it. So it'll push the J counter up to 4, right? And then it resets I. So I has to go from 1 to 4. And then finally it gets up to 4, and now everybody is up to the maximum, and I have to go to the next K value, right? So 5, these get reset, and I'll have to go from 1 to 1, and then J will go to 2, and I will go from 1 to 2, and then J will go to 3, and then I will go from 1 to 3, etc. And so what's happening is you're enumerating the multi-set for that particular case, and it turns out then, like I was saying, it's dependent on this n value and the number of loops. Okay, so in general, it'll be the number of executions will be your n value minus 1 plus the number of loops, where n is the maximum value for k. So maybe that's the max value for k, and then choose number of loops. Okay. So the last type of problem in my notes, and then we'll look at some WebAssign problems, is these solutions to equations like this x1 plus x2 plus x3 plus x4 equals 10. Okay. In this case, we want non-negative integer solutions. So x sub I is in the non-negative ints, which means it's in the set 0, 1, 2, etc. Okay. If it asks for the positive integers only, you exclude 0. Okay. And I'll show you an example of that next. But in this case, what you're doing is just throwing ones in for every box. Okay, so there's 4 boxes, in other words 3 slashes, and the x's represent ones, so there's 10 ones. So I could put a couple here, let's put a couple here, and then maybe one here. Okay, so one particular solution to this problem would be 3 comma 5 comma 0 comma 1, right? 3 plus 5 plus 1 is 10. So the way this will work in our calculations, the number of bars is the number of x's that you have being added together, minus 1, right? So we have 4 unknowns that we're adding together, the x1 plus x2 plus x3 plus x4, then subtract 1, plus the number on the right hand side of the equation, which is 10, and then choose 10. Okay, okay, so let's move on to WebAssign problems, and in particular let's look at one a little more complicated, like number 5. So find all possible solutions to x1 plus x2 plus x3 plus x4 equals 29, where in this case x sub I needs to be a non-negative integer. Okay, is well, no, that's what we did last time, right? So let's look at a different one. Let's look at number 4. Find the number of possible solutions to x1 plus x2 plus x3 equals 24, where the xi's now in this case are in the set of positive integers. Okay, and what that means is, and sometimes they write this out as just z plus. Okay, whereas before we included 0, right? So, and sometimes the books will write this as z. In our book, they write it literally non-negative, but I don't think it's very helpful to write it like that. What's more helpful is to write it with a plus up here and a 0 down here. So you're including all the positive numbers and you're including 0. Okay? So in this case, we're not including 0 for our solutions. In other words, when you go and kind of set up your scenario, it's kind of like you've already picked root beers, right? You've said, all right, there's already one a guy in here, there's already one guy in here, and there's already one guy in here. So you'll never have 0 in here. So in other words, x sub I is not equal to 0. And now in this case, you're left with 24 minus 3 x's to put into the boxes. In other words, 21 elements. And so we have our 3 possibilities, of course 3 minus 1 for the 2 slashes, and then the number of x's we're putting in, there's 21 of them, right? So it would be 3 minus 1 plus 21, choose 21. So it would be 23, hopefully choose 21 at the end of the day. Okay, so let's go back now and look at a more complicated version of the Coca-Cola problem with the number of cans of Coke or Sprite or whatever. In this case, number 7, the store sells 8 colors of balloons. Sorry, my English spelling is terrible. Colors of balloons with at least 31 balloons of each color possible. Okay, how many different combos of 31 balloons can be chosen? Okay, so in this case, we're basically putting x's into the color slots. So how many color slots are there? There's 8. In other words, there's 7 slashes, right? So 1, 2, 3, 4, 5, 6, 7. And then we're plopping in 31 x's. So at the end of the day, and I don't want to go through that, let's just write it out. So it's 8 minus 1, okay, the number of slashes, plus 31 for the x's, like maybe I got 2 blue balloons, 3 of the red balloons, and let's not go through it, right? All right, so and we're choosing 31 of those. Okay, so this would be 38, choose 31. So that's a total. Part B, now they start throwing some restrictions at you. So say the store has only 12 red balloons. And again, the question is how many different combinations of 31 balloons can you have? So this is one of those ones where you want to do a subtraction. You're going to figure out how many combinations have 13 or more red balloons. Okay. And that's the game where you're already setting 13 balloons to be in a slot. You're already kind of throwing away 13 of your x's. Okay, so you'll have 31 minus the 13 of your x's. 31 minus 13 gives you 18 x's to kind of put in the slots. So again, how many slots are there? There's going to be 8 minus one of those, and then we're placing 18 X's in there. Okay. So the number of combinations with 13 or more red balloons will be 25, choose 18. Okay. So the number of combinations where there's 12 or less, quite naturally, then will be just the total number of different combinations where everything goes, minus the number where you have 13 or more. 13 or more red. Okay. In which case, this means we have 38, choose 31, minus 25, choose 18. Okay. Part C, similar question, but now they're saying, oh, we have a restriction, only 8 balloons, only 8 blue balloons. Okay. Okay. All right, so it's the same game, and you can almost figure out how to do this. So 8 or less means we take the total and subtract away 9 or more. Okay, so that's just going to be the 38, choose 31, and then subtracting away 9 or more. So we need 31 minus the 9 we're kind of throwing away, which is 22. And we'll go 8 minus 1 plus 22, choose 22, right? So 7 plus 22 is 29, choose 22. Okay, now part D is the hard part. They say that the store only has 12 red and 8 blue. Um, 12 red and 8 blue. Okay, so the hard part is kind of figuring out how to count up the number of scenarios where you have 13 or more, and or 9 or more. Okay. And you have to think in terms of sets. Right? So this is going to be basically the 13 or more plus the 9 or more minus the 13 or more and the 9 or more. Okay. Okay. Okay, so we know the first two from part A and part B. This is part A, this is part B. Or whoops, this is part B and this is part C. The thing we don't know is this 13 or more and 9 or more. But that turns out to be pretty simple. 13 or more and 9 or more. To figure that out, you're just going to kind of throw away 22 of the X's, right? So that's the case where, all right, so we have 8 minus 1 for the slashes, and then plus 31, and we're throwing away the 9 plus 13, which is 22. Okay? So 8 minus 1 plus 9, and then we're choosing 9 of those. So that's going to be 16, choose 9. And then that would go right into here. And so finally then, to figure out 12 or less and 8 or less, we take the total and subtract away the 13 or more or the 9 or more. Okay. And of course that'll turn out to be 38, choose 31, minus The again, it's part I believe it was part B. Okay, so 25, choose 18. Plus the part A. Okay, so the first one from part B, 25, choose 18. The second one is 29, choose 22. I mean, it wasn't the answer from part A. It's part of, this is part of part A. So I shouldn't say it was the answer from part B. 13 or more wasn't the answer. It was 12 or less was the answer. So but the answer we're looking for was in part B in particular. It's sitting right here. We need this, and from part C we need this. Okay, sorry about that if that wasn't clear. So plus 22, and then minus the intersection, which we just figured out here in part D, 16, choose 9. Okay, let me get the color back. Okay, so that's a hard one, and I promise I won't put it on the test. I may, if I do put it, it's an accident, and I mean to put it, and just say something to me, and I'll get rid of it for future generations, so I don't have to put them through such torture, right? Okay, that'll do it for now, and we'll see you in the next video.